All right. Okay. Let's see if we can design a logic gate. Let's try to see what we can come up with, and then we'll associate the name of the gate with this. So let's see what we can do with one transistor. So I'm going to start drawing a transistor based net circuit, one transistor, and let's see which gate we end up with. So let's say I have a transistor, the symbol is that. I've got the base terminal there, I've got the collector terminal there, I've got the emitter terminal there. I'm going to connect the base to, so that base is my control. So I'm going to connect the base terminal to an input voltage, and let's call that Vx. And I'm connecting that using a resistor R. It could be some 1 kilo ohm value, say. That is essentially going to limit the amount of current that flows into the base terminal. Next, let us just connect emitter to ground and connect collector to a high voltage, say for example 5 volts, and we'll try to monitor the voltage at this node. Let's call it Vy. So I've got a transistor over here. Perhaps I can put this over here. I've got a transistor. The base terminal is being controlled by Vx. I have the collector terminal, which is where I'm monitoring the output Vy, and I'm also connecting the collector terminal to a plus 5 volt voltage supply, a DC supply, with another resistor. And because that particular resistor is pulling the voltage up to a high value, I'm going to call that resistor a pull up resistor. Say 1 kilo ohm pull up resistor. Now let's see how this is going to operate. And I'm looking at this in an extreme situation. So when Vx is low and when Vx is high. So let's establish a table, and we are going to try to monitor the voltage X, and we'll monitor the voltage Y. And just so that we have the state of the transistor being monitored in this table, we'll also label this transistor, say, as Q1, and we'll have Q1 state being monitored as well. And because we are looking at the two extreme situations, we could have a low input for Vx, or we could have a high input for Vx. If we have a low input at Vx, it means that it is not enough to turn on this transistor Q1. And if it is not enough to turn on the Q1, there is an open circuit between collector and emitter, which means that there is no path for Vy, there is no way that Vy can read ground 0 volts. Hence, it has to read 5 volts. So Q1 in this case was off and Vy is high. In the other case, okay, let's see here, there's some issue with my screen sharing app. Okay, In the other case, I have Vx to be a high voltage. So if Vx is high, it probably is enough to turn on Q1. So we have Q1 to be on. If it is on, it means that we have a short circuit between collector and emitter. They are both connected now. And Vy is essentially at the same potential as ground. So which means that my Vy is going to read low. So I can translate this uh, table into a truth table. So I'm going to use X that represents the voltage Vx, but X is a binary variable now. In the output, I'm going to use Y. 0 for low, 1 for high. In the output is high and low. So this is a NOT gate. Symbol, triangle followed by a bubble. X is the input, Y is the output. So what I did was essentially design a NOT gate using a transistor. So to build a NOT gate, I need one transistor, one BJT transistor. All right, let's now try to see if we can design a buffer. Well, we have already established that a buffer is equivalent to two NOT gates. Because if I can do that with one transistor, there's nothing there's nothing else for me to do. I need two NOT gates back to back to make it into a buffer. So how can I do that? Well, I would need two of these. So I will copy this from here and try to paste two copies of the same guy over here. But what I'm going to do is I'm going to connect the output of one to the input of the other as such. And I'm going to clean things up a little bit. And what I have is a buffer where my original input is Vx and my final output is Vy, and this is essentially my intermediate output, say V out 1. So by having two transistors back to back, I was able to design a buffer. So essentially what happens is, even if, and we said that a buffer is sort of regenerating that level, that regeneration is able to happen because at V out 1 we have this 5-volt supply that takes a low and makes it into a high, and we have another 5-volt supply that allows the one input and make it into a zero. So by doing that operation, I'm able to sort of regenerate that logic level. So I need two transistors back to back here. Next, let's see if we can design AND gate. Well, for AND gate, we associated the term switches in series with AND. So let's see if we can put some transistors in series and are able to design an AND gate. And let's start with a two input AND gate. So let's see, I'm trying to look at a two input situation. So I need two transistors in series. So let's see if I can have one transistor here, and I'm going to connect it to another transistor right here in series. And I'm going to pull this up to 5 volts using a pull up resistor, and I'm monitoring the voltage Vy over here. I have Q1 and Q2 as two transistors. The base voltage is being controlled by Vx1 and say Vx2. and I'm going to connect ground to the emitter of this transistor. So I've got one transistor there and I've got one transistor there, and they are in series. So let's see what happens with this transistor configuration. I'm hoping that it turns out to be an AND gate. Let us verify if it really does. So in order to analyze this, I need a column for Vx. Actually, let's just go one step ahead and call it x1 and x2. Um, if I need q1, all right, let's stick with Vx1, Vx2, q1, q2, and the last one is say Vy. These are my inputs. Those are going to be the state of the transistors, and finally I have the output. So Vx1 and Vx2 are controlling transistors Q1 and Q2 respectively. And because I have two of them, I will have four possibilities for these two voltages. So let me write it as low, high, two lows and two highs. Next, Q1 is going to be on and off depending on Vx1. So if it is low, it will be off, and when it is high, it will be on. And Q2 will do the same, but with respect to with Vx2. So off here, off here, and on here. Now Vy, when will Vy read 0 or low? The only way Vy will be able to read low is if Q1 was on and Q2 was on. Both of them have to be on because they are in series for it to be 0. You're right, Derek. So let's see. When is Q1 on and Q2 on? Well, it's only the last one. So the last entry in the table is the both transistors on entry. So only then Vy can read low. Otherwise, if even one of them is off, Vy will not be able to read low. It will have to read high. So it will be high, high, high for these three cases, which means I have an output which is giving me high, 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 low, or 1, 1, 1, 0, which is exactly the opposite of AND, because in AND, if you look back, your output column for the same set of inputs was 0, 0, 0, 1, and for NAND, you had 1, 1, 1, 0. Which is what we have over here. So this is in fact a NAND gate is what we have designed. So a NAND gate, a two input NAND gate is has two transistors. So the question next is how do we get AND? Well, there is no such thing as AND. We will have to build it using NAND and NOT. So I am interested in AND gate next, and I'm going to build it by putting NAND first and then goes into a NOT. I have designed NAND over here. So let's copy this guy, paste it over here. I've got NAND followed by a NOT that I need to bring in from the first slide. Now we have Vx1, Vx2 are going in, Vy is coming out. So this is my two inputs, one output, and I have Vout1. Vout1 is giving me NAND here, and when I do the NOT, I get AND. So here Y is X1 and X2. Out1 is X1 NAND X2. So by building it in two stages, I was able to design a AND gate. For a two input AND gate, which is what we have over here, so this equals this. Two input AND gate with X1, X2 and Y, I've got three transistors. Q1, Q2, oh my gosh. Okay, let's be a little bit careful with this. Let's make this Q3. Okay, so that's an AND gate. Next, story is going to remain the same but complementary when we talk about NOR and OR. So for NOR gate, we need switches in parallel. So let's put two transistors in parallel to design a NOR function. So I've got one transistor right here, say Vx1, controlling the base. This is Q1. And another transistor that is going to be in parallel. So I've got Vx2 resistor goes into the base of the transistor, ground terminal there, and collector terminal. They are in parallel, so I'm going to connect the collector terminals of both of them and then pull them to a high voltage using the pull-up resistor. This is say Q2, this is say Vx2. So those are my two transistors. What else? And I'm monitoring my output right here. That's going to be my Vy. So in this case, Y is going to equal X1 nor X2. And you can verify that by going through the steps very similar to what we have done before. Symbol, two input, NOR gate, X1, X2 and Y. Two transistors. Switches are in parallel. Next, for OR, we are going to have NOR followed by NOT. The same sort of thing that we did for AND gate. So we simply add a NOT gate in front to make that happen. All right, so that's all I had for you guys in terms of the lecture material. Let us stop the recording and then we can discuss where we go from here.